The graph of a log function, where the base is some number greater than 1, which would include our base e, looks something like this. And a log function where the base a is between 0 and 1 is going to look something like this. So some properties of log functions that we can discuss based on these graphs is the domain is 0 to infinity. So in both of these situations, the graph stays to the right of the y-axis, which means we can only plug in positive numbers to a log function. But the range is all real numbers, and you'll notice that that is exactly the opposite of what we had for our exponential domain and range, and that's because of the inverse relationship between the two. Now both of these graphs, as x gets closer to 0, the graphs are getting closer and closer to the y-axis, but never actually touch or cross the y-axis, which means that the y-axis, or the line x equals 0, serves as a vertical asymptote for these functions. And also because it never touches or crosses the y-axis, it means that these graphs are not going to have any y-intercepts. But the x-intercept is going to be 1, 0. So this point in both of these graphs is the point 1, 0. Now to graph a log function for a specific base, we're going to approach this very similar to how we graphed our exponential functions, which was plugging in numbers and plotting points. The only difference now, though, is you'll notice that I already have the y column filled in instead of the x column. So what we want to find for each of these is where the log base 2 of x is equal to each of these values. So the first one will be, where is it equal to -1? And the reason why I'm plugging in y values instead of x values is because we can rewrite this as an exponential equation that makes it easier to evaluate. So just using our definition of logarithm, this is the same as 2 to the -1 is equal to x. And then 2 to the -1 is the same as 1/2. So when x is 1/2, the log base 2 of x is equal to -1. And it's going to be similar for these two. If we're trying to find where log base 2 of x is equal to 0, that's the same as asking 2 to the 0 is equal to what? Which is 1. And where is log base 2 of x equal to 1? That is equivalent to 2 to the first is equal to what? Which is 2. And now we have this collection of points that we can graph. We've got 1/2, -1, 1, 0, and 2, 1. And when we connect those, we see that we end up with a graph that looks like this for log base 2 of x. So we're going to do something similar for the log base 1/3 of x. When is the log base 1/3 of x equal to -1? Well, that's the same as evaluating 1/3 to the -1, which is 3. And where is log base 1/3 of x equal to 0? That's the same as evaluating 1/3 to the 0, which is 1. And where is log base 1/3 of x equal to 1? That's the same as evaluating 1/3 to the first, which is 1/3. So then plotting these points, we have 3, -1, 1, 0, and 1/3, 1. And when we connect those, we can see that we end up with a graph that looks similar to this one. And then what does the graph of the natural log of x look like? Well, remember, this is understood to be base e, so if we're trying to figure out where natural log of x is equal to -1, this is the same as evaluating e to the -1, which we said is approximately 0.4. Where is natural log of x equal to 0? This is the same as evaluating e to the 0, which is 1. And whereas natural log of x equal to 1, this is the same as evaluating e to the first, which we said is approximately 2.7. So then we plot these points, 0.4, comma, -1, 1, 0, and 2.7, comma, 1. And we end up with a graph that looks very similar to our log base 2 of x.